Okay, I have two more examples dealing with this. These ones get a little more difficult. So a child throws a 0.200 kilogram rock at a tree. When the rock leaves the child's hand, it's moving at 20.0 meters per second, and they're located 1.5 meters vertically above the ground. Determine the height that the rock is at when it strikes a tree if it's moving at 10 meters per second. So obviously it lost some energy. So at the moment of impact, what is the height above the ground? Apologize, it's so long there. No solution, so let's draw a little diagram here of this little prankster throwing rocks at trees. Maybe he's looking for a squirrel or trying to hit a chupacabra, who knows. So here we have the kid, that rock in his hand is 1.5 meters above the ground. So obviously this diagram isn't to scale because that looks like a lot more than 1.5. Either that or it's a small kid. Throwing the rock at a tree. So the situation before is the rock is leaving the kid's hand after it's hitting that tree. Analyze the before and after, see if you can figure it out. So total energy before equals total energy after. Kinetic energy before plus potential energy before equals kinetic energy after plus potential energy after. Now up until this point I've been talking about anything that's raised up has this gravitational energy applied to it. But in this case we're told that it has kinetic energy too. The rock has some speed behind it. So I can't say that that's zero. In fact, I can't say any of these is zero because at this point the kid's throwing the rock, so it has potential and potential energy and kinetic energy. When it hits the tree, it's off the ground, so it has potential, and it also has a speed which we're figuring out, so it has that as well. So the best we can do is break everything down here. Oops. So in terms of labeling before and after, B for before, A for after, what makes kinetic energy different before and after is the speed or velocity. The thing that makes gravitational potential energy different before and after is the height. So HB, HA, VB, VA. Okay? And of course, what I'm looking for is, what am I looking for? Determine the height that the rock is at when it hits the tree. So this is what I'm looking for. HA. That is what my variable is that I need to isolate. So what I do here, instead of substituting everything in, I rearrange the equation first. And I recommend you do that too. So I have mgh plus 1/2 mv squared. So the opposite of plus is subtract. So subtract 1/2 mva squared. Subtract 1/2 mva squared. To move that to the other side. And I get that. So I'm left with, let's just see here, let's cross it out here. So boom, it's gone. And I'm left with 1/2 mvb squared plus mghb minus 1/2 mva squared. And of course you can see something here. I have something that's common in all three of these terms. What is it? It's mass. So that's, I'm just going to factor that out. Factor out the m. M times 1/2 mv squared, m times GHB gives me that, m times that, so hopefully you remember factoring because that comes into play here. Okay, so I'm solving, for, once again I'm solving for HA, so I want to get HA by itself, and of course I have m and g with it here. M times g times h, so of course to undo multiplication you have to divide. So divide by mg, divide by mg. So you can see the m's cancel, the g cancels, I'll end up with HA on the right. Interesting thing over here, m will cancel because this is mass times all of that what's inside the brackets. It cancels. So that's a specific note. It doesn't matter what the mass is because I don't end up using it in the final equation here. So it's not dependent upon mass. Hint, that's a question I think I gave you in one of the textbooks to look at. So all I'm left with here, I have the equation rearranged for HA. Hopefully you can handle that. I think you can. I have velocity before, g, height before, velocity after, and I know all those things from the question. So it's just a matter of substituting in So it looks more complicated than it actually is. A half of my velocity before, 20 meters per second squared, 9.8 times 1.5. I'm told that the speed after as it hits the tree is 10. So working all that, see if you can put that in your calculator, get it to work out the height. Well, I guess I had another step in here too. Don't forget squared, 20 squared times a half, etc., etc. You should end up with, when all is said and done, 16.8 meters. So be sure you work that out. Make sure you can get that. Make sure you have the order of operations right in order to get that 16.8 meters. Okay, I have one more example here. I think I'm going to leave it for the next video because this one was fairly lengthy. So the last one deals with the snowmobile going off a cliff. Super exciting, almost as exciting as this one.